I want to start our study of logic in Chapter 3 with Section 3.1, which is called Logic Statements and Quantifiers. The field of logic is very important to our world today because all of the integrated circuits in all your devices that you're probably holding in your hands or have on your table right now would not work without the logic etched into those integrated circuits. In any case, let's start off by talking about what we mean by a statement in logic. Every language has different types of sentences. You might call them statements or questions, commands, there might be others. For instance, if I said, "Is the test today?" that's a question. If I said, "Go get the newspaper," that's what I'd call a command. If I said, "This is a nice car," that's really my opinion. If I said Denver is the capital of Colorado, that's pretty much a statement of fact. Those last two you might sort of contrast with what we were talking about with well-defined sets. When I say it's a nice car, someone else might not agree with that. That's really just my opinion. Whereas Denver is the capital of Colorado, that's pretty much just a fact that everyone would have to agree to. And that's sort of like we were talking about with sets being well-defined or not. It's the same type of analogy. In any case, George Boole, the mathematician, was instrumental in getting these kind of things going and building the basis for this study of symbolic logic, which, as I said, is very important in today's world. Nothing in our hands that we use day to day walking down the street would even work without this symbolic logic being etched into those integrated circuits. But it applies to mathematical or logical statements. And here's our definition of a statement. A statement is a declarative sentence that is either true or false, but not both true and false at the same time. For example, if I said Florida is a state in the United States, I think all of us would agree, yes, that is a declarative statement. I'm declaring something about the state of Florida. And in this case, it's actually a true statement. Statements do not have to be true. How are you? No, that's not a statement. It's not declaring anything. It's asking a question. That is not a logical statement. 9 to the 9th plus 2 is a prime number. That's a declarative statement. It's stating something that's either true or false, but not both at the same time. Now, I may not know whether it's true or false, but I can still say for sure that it is a logical statement. This one might be a little tricky. X plus 1 is equal to 5. That's what we call an open statement. It's a little tricky in the sense that it depends on the value of x. So the way you have to think about these open statements, these equations with variables in them in this case, is that for any particular value of x, this statement is either true or false, but not both at the same time. For instance, if x equals 4, I get 4 plus 1 is equal to 5, and that is a true statement. On the other hand, if I let x be anything else, say 0, I get a false statement. But it's an open statement in that it depends on the value of x, but once you've chosen a value of x, it is either true or false, but not both at the same time. So we say that is a statement. Then we get to the idea of a simple versus a compound statement. A simple statement is a statement basically that just gets across one single idea, whereas a compound statement conveys more than one idea. That's sort of a general way to think about it. These statements are connected with things we're going to call connectors. In the English language, the word and is a common connector, or is a common connector. The phrase if then is a connector, and something maybe you don't see quite as much, the phrase if and only if. Those are the most common connectors that we use in logic. You use those connectors to make compound statements out of simple statements. For example, if I said I will attend the meeting or I will go to school, that's a compound statement because I take this simple statement conveying the single idea that I will attend a meeting, along with the simple statement, I will go to school, put them together by connecting them with a connector, in this case the word or, and I get a compound statement. So I can use these connectors to create compound statements from simple statements. We'll use these symbols to represent the various connectors. And these are the common symbols, and I want to go over them one at a time. I didn't mention this earlier, but the word not can also be considered to be a connector, and the symbol for not is the tilde, a little squiggle. So if I have a statement P and I want to say not P, I can consider that to be a connector. It's a little different than the other four connectors we talked about earlier because it's not really connecting two simple statements. It takes a simple statement and turns it into a compound statement without a second simple statement. In a sense, the not is different than the other connectors. In a real sense, it's simpler than the others as well. So you can take a statement and say not that statement. And that not is considered to be a connector called the negation. Talked about and. If you want to take two statements and connect them with the word and, we use the symbol here, which is basically an upside down V. And we call that a conjunction. The word or, the symbol is a V shape. We call that a disjunction. If then, again, is a connector we talked about earlier. The symbol for that is a rightward pointing arrow. An arrow pointing to the right is the symbol for the connector if then. It's called a conditional. And the fifth one is the if and only if. P, if and only if Q. The symbol is an arrow pointing in both directions, and that's called a biconditional. So conditional is an arrow pointing to the right. A biconditional is an arrow pointing in both directions. And you'll have to learn those 5 connectors and the symbols for them. Now we're getting down to the heart of the matter. Once we start talking about statements, simple, compound, very complicated statements in some cases, what we want to look at is the truth value of those statements. So if you've got just a simple statement, it's going to either be true or false. That's pretty straightforward. The truth value of a compound statement, however, depends on the truth values of all the simple parts of it. So you have to take the compound statement, break it up into simple statements, look at the connectors, and decide overall is that statement true or false. So it's the same idea, but it's a little more work because you're having to analyze each individual simple statement first. The idea of a truth table is to take usually a complex mathematical statement and analyze its truth value for every possible combination of how the simple parts of it turn out to be. If one part of it's true, the other part's true, is the overall statement true? If one part's false and the other part's true, and so on. So a truth table tables all the possibilities of what the simple parts of a compound statement could be and analyzes their truth values and puts the results into a table. We'll talk about that more later. But let's just take these connectors and go through them. For instance, let's start off with the negation, the not. Let's look at that. If I said today is Friday, the negation is pretty simply today is not Friday. If I just used a symbol instead of an actual English language statement, I could call a statement P, and its negation would be not P using the tilde or the squiggle in front to the left of the statement P. That's how I would say not P. Now, this probably is just common sense, but I do want to spell it out. If a statement is true, then its negation is automatically false. If the statement is false, its negation is automatically true. A statement and its negation always have the opposite truth values. Common sense. Another example. Ellie Goulding is not an opera singer. If that's the statement, the negation would be Ellie Goulding is an opera singer. So the negation of a statement said in a positive way has the negative, a not. If something starts out with a not, its negation sort of gets the not removed. We'll be working a lot with compound statements in symbolic form, so you might as well get used to this. Let's look at this. So I might have a statement that says today is Friday, and I'll give it a name. I'll call it P. That way, when I refer to that or write it down, I don't have to write the whole statement down. I could just write down or say P. Another statement might be it is raining. I could call that Q. Third statement, I am going to a movie. I could call that R. Finally, I am not going to the basketball game. I could call that S. Notice that the not is in that statement for S. So if at any point I need to negate S, the negation of not going to the basketball game would be I am going to the basketball game. So that's a little careful there. So let's do something. What if I said to write this in symbolic form, today is Friday and it is raining? First thing you want to do is look at the statement, today is Friday. I gave that the name P. So I would want to put P down as the symbol for that statement. Then you've got and. Remember, and is the upside down V. So you're going to write that down. And finally, it is raining is Q. So I'll write that down. So the statement would be P and Q, where the and is represented by the symbol for and, which is an upside down U. Here's another. It is not raining and I am going to a movie. Well, this time I'm still using and, so I'm using the upside down V, but now I'm negating the statement, it is raining. So if I want to negate it is raining, that of course will be it is not raining, which is not Q. As I said, the and is still being used, so it's an upside down V, and I am going to a movie, which is the R statement. So the symbolic form would be not Q and R. Another one, I am going to the basketball game or I'm going to a movie. This time we're switching connectors and we're going from and to or. So and is an upside down V, or is the V shape. And I am going to the basketball game is going to be the negation of I am not going to the basketball game. So that will be not S. And as I said, the or is a V shape. And I am going to a movie is R, so it would be not S or R. So I hope you're getting the hang of this. It's just mainly a matter of being careful. One more. If it is raining, then I am not going to the basketball game. Okay, this time we have an if-then, and an if-then is the conditional, which is a right-pointing arrow. It is raining is the statement Q. And remember that symbol is that right-facing arrow. It is raining becomes Q. The symbol for if-then is the right-pointing arrow. And then I'm not going to the basketball game. Remember, the not is already built into the sentence S, so it's just S. It's not S. Those are the little tricky things you've got to be careful about. Try another. We've got 4 statements. The game will be played in Atlanta as P. The game will be shown on CBS as Q. The game will not be shown on ESPN as R. The Mets are favored to win is S. And let's write those as symbols. Start out with the statement Q and P. Remember, the upside down V is an and. And now let's take that symbolic statement and translate it back into words. Well, the statement Q is the game will be shown on CBS. The upside down V is an and the game will be played on CBS is the P, so there you go. Piece of cake. Second one says not R and S, so the negation of R says the game will not be shown on ESPN, so the negation will be the game will be shown on ESPN. S says the Mets are favored to win, and you want to connect them with an and. Simple, right? The line with arrow on both sides in both directions is the if and only if. So S is the statement the Mets are favored to win. P is the game will be played in Atlanta. So not P is the game will not be played in Atlanta. So it will be the Mets are favored to win if and only if the game will not be played in Atlanta. So once you understand the basics of this, it's sort of like playing a little game, and it's really pretty easy if you're careful. We talked about this already a little in a slightly different context, but in mathematics we use parentheses to indicate groupings. The English language is not quite as precise as mathematics, so what we're going to do is go through this and talk about it explicitly so there's no confusion. So if I put two things together inside of parentheses, I'm saying they're grouped together. So in this case, Q or not R are a grouping. They're thought of together. In the second one, the P and Q are together, are grouped together. And in the last one, you've got P and not Q grouped together, but you've also got R or S grouped together. Now, what does that mean for us? Basically, means that you're going to work inside the parentheses first before you move outside the parentheses. This goes back to something we talked about earlier. Since the English language is not quite as precise, we're going to use commas in place of parentheses in our English sentences. So if I want to indicate a grouping, I'm going to put a comma in so that everything on one side of the comma is considered to be grouped together. So it's easy to see. If I take P, comma, and Q or not R, then what I'm going to do is I'm going to consider everything to the right of the comma, which would be the Q or not R, to have parentheses around it, to be grouped together, because they're on the same side of the comma. That comma is giving us grouping information. That's the way we're going to think about this. On the other hand, if I had P and Q, comma, or R, then again that comma is telling me everything on one side of the comma is grouped. In this case, P and Q would be grouped together. So they would have commas. So we think of that comma as a way to translate an English sentence back into the mathematical symbology. And it's telling us where to use parentheses, basically. One more. If P and not Q, comma, then R or S. Again, everything to the left of the comma is grouped, and since there's more than one thing to the right, then everything to the right of the comma is also grouped. So the P and not Q are grouped together. Other side of the comma, the R or S is grouped together. This is going to be our convention, so you need to focus on this and get the idea in your head, and then it's easy. Conversely, if you've got a statement written as an English sentence, you're going to be able to go back and forth, in other words. So if I give you a statement P that says you get a promotion, a statement Q that says you complete the training, and a third statement R which says you will receive a bonus, I could ask you to write all sorts of things as English sentences. For example, P and Q grouped together with an if-then symbol, are. In other words, if P and Q, then R would be the way you'd read that. Because that P and Q appear in parentheses, that means when you write it out in symbolic form, you're going to place those to the left of a comma when you write the English sentence. So remember, the right pointing arrow is if then, so it's going to start off if. If, then you take the statement P and Q. Well, the statement P is you get a promotion. Then you've got the symbol for and then you go to the statement Q, which is you complete your training. So that would be, you could write that sort of in a ragged kind of sounding way, if you get a promotion and you complete the training, or you can kind of just leave that second U out and make it sound better. If you get a promotion and complete the training, you could put that second U in if you wanted to. And then finally, as I said, the right-facing arrow is an if-then, so you've already got the if written down, so you now write the then down and finish off with whatever the statement R says, which in this case, R says you will receive a bonus. So there you go, you will receive a bonus. If you get a promotion and complete the training, then you'll receive a bonus. It's not hard, you have to be careful. Remember that arrow facing to the right is the symbol for if-then. Okay, let's take this sentence. If you do not complete training, then you do not get a day off and you do not get a bonus. So if you're going to turn this back into symbolic form, then you've got to look at that comma. That comma comes after the statement, you do not complete training. So everything to the right of that comma is going to be grouped together. If you look at it, you do not get a day off is the negation of you do get a day off. You do get a day off is P. So you do not get a day off will be not P. And of course, you complete training is the negation of you do not complete training. So that will be not Q. And then you get a bonus. The negation of that is you do not get a bonus. So that would be not R. Everything to the right of this comma is going to be grouped. There's only one thing to the left of the comma, so you don't have to worry about that. So when you put this all together, you get the not Q. There you go. And it's an implication, so that's the if-then part. And then as we said earlier, the not P and, which is an upside-down V, not R are grouped together to the right of the if-then symbol. So when it's all said and done, you get this translation. The key to the whole thing and knowing how that grouping works is finding the comma and working with it. It's not difficult, but you do need to practice. Now here's where it gets a little more complicated, and I'm going to ask you to focus and think. If you'll do those two things, this is not so hard. But English is a very vague language. We speak in mathematics very precisely, but when you speak in the English language, we are very loosey-goosey with a lot of things, and that's what you'll find here. So sometimes you'll take a sentence in English that can be translated more precisely into symbolic logic form, but you've got to think about how to do it. The best way to see it, I think, is just through an example. For example, I might say, rewrite the statement, any shoe in my closet is a size 10. Rewrite that as an implication. Now, implication means an if-then, which means I'm going to have a right-facing arrow or a right-pointing arrow in my solution. Now, in your mind, you need to think about what that statement means. Any shoe in my closet is a size 10. That sounds like just one statement. So how are you going to make an implication out of one statement? But if you think about it a minute, the English language has really packed two separate ideas into one sentence. So you sort of have to undo that and break it back into two ideas. And there are basically two ideas here. You know there's going to be an if something, then something. So somehow that single sentence has to have two ideas in it, or you can't possibly do what they're asking you to do. So at this point, you're trying to think, how can I take this single sentence and somehow rewrite it so that it actually has two ideas in it, which gives me a shot at turning it into an implication? Well, think about it. This is basically telling me that I have a shoe in the closet, or there are shoes in my closet. So one idea has to do with there being shoes in the closet. And the other idea is about the shoe being size 10. So this one thing that seems to be just a single sentence, well, it is a single sentence, is actually composed of two basic ideas. Remember, we talked about a compound statement had more than one main idea in it. And this is what you've got to think about. This sentence has to be broken back into its two ideas. Any shoe in my closet is saying something about there being shoes in my closet. It's also saying something about shoes being size 10. So once you get beyond the idea of what in the world am I supposed to do, you've got to think it through. I've got to take this seemingly one sentence, break it into two ideas, and then put it back together with an if-then so that it says the same thing as the original statement, or it means the same thing as the original statement. So I would say this any shoe in my closet is size 10 can be broken down into two simpler sentences. A shoe is in my closet. The other would be the shoe is a size 10. So you got the idea of there being shoes in the closet, the idea about them being size 10. Now, once you get there, you're sort of home free, because the sentence, a shoe is in my closet, will either go in the first position or the second position, and the second one's either going to go in the first and the second. So if the first one goes in the first position, then the second one goes in the second position. If the second one goes in the first position, then the first one goes in the second position. So really, you just got to try it both ways and see which one of them preserves the meaning of the original sentence. So let's just try sticking them in and see. If I just keep them in the, just throw them in there. Say if I say the shoe is a size 10, in other words, what if I decided to put the shoe is a size 10 first, then it is in my closet. Again, you're going to sort of work around with those sentences so that it doesn't sound quite so stilted in English. So you could say if the shoe is a size 10, then a shoe is in my closet. That sounds sort of weird, so you sort of make it sound a little better in English. So I might say, if the shoe is a size 10, then it is in my closet. Now you're saying, well, is that the same thing as the original statement? If I say any shoe in my closet is a size 10, is that the same thing as saying if the shoe is a size 10, it is in my closet? Think about that a minute. That's pretty much saying any shoe in the universe that's a size 10 is going to be in my closet. That's sort of what that sentence is saying. And that's not what the original statement said. The original statement said any shoe in my closet is a size 10. It doesn't say any size 10 in the whole universe is going to be in my closet. That'd have to be one massive closet. So that's pretty much easy to see that that's not the same meaning. You're not preserving the same meaning. At this point, if you're sure about it, you really know what the answer is, but let's just switch it around and see that it does seem to mean the same thing. So I'll switch it the other way, and now I'm going to put them in different order and say now, if a shoe is in my closet, then it is a size 10. And then read the original statement again. Any shoe in my closet is a size 10. In other words, if I walk into that closet and see a shoe, it's going to be a size 10. Well, isn't that pretty much what that statement at the bottom now here says? Isn't that about what that says? If a shoe is in my closet, it's a size 10. I'm not going to belabor this too much because you've just got to think this through yourself, but the answer is, yeah, that's the same meaning. So what I've done now is I've converted that English statement that we started with that seems like it's just one statement. I've broken it into two simpler ideas and written it in an equivalent form as an implication. That skill is going to be important sometimes to us, so you need to practice doing it. It's not difficult, but you've got to understand what you're trying to do, and then be sure once you get the two simple ideas, you try them in both orders and see which one of them preserves the original meaning of the statement. And that's all my advice I have beyond that. You just have to practice. And once you do that, you could also convert it back into symbolic form. So if I wanted, once I got the answer the way I wanted it, if I took that, if a shoe is in my closet in size 10 and wanted to give it symbols, I could take the first sentence and call it P, and the second one call it Q, and then I could convert it back into a symbolic statement that says P implies Q, or P, if P then Q. So not very difficult, but you do have to think about these things. Now, I referenced at the very beginning the idea of truth tables. So this is where we're actually going to talk about building truth tables. So let's just take these symbols one at a time and build truth tables for them. Simple idea, let's just go back to the common sense meaning of words in English. If you order cake and ice cream in a restaurant, you're expecting to get both. And that's sort of the way the word and works in logic. So the statement P and Q is true if both of them are true, and false if either is false. In other words, if the waiter brings you cake and ice cream, then he has, in that sense, told the truth. He's given you what you asked for. If he only brings you cake but not ice cream, or if he only brings you ice cream but not cake, or if he doesn't bring you either, then in that sense it's false. He did not fulfill what you asked for, so in that sense it's false. So what you can say is there are really four possibilities. The waiter could bring you, if you're looking at this as being, maybe look at the P as being cake and the Q as being ice cream, the waiter could bring you ice cream and cake. He could bring you ice cream but not cake, or she, cake but not ice cream, or neither. So if you think about it in that sense, it's pretty easy to see what the truth values are. If you get cake and ice cream, the waiter fulfilled what you asked for, so that would be considered to be true. But if the waiter brought you ice cream or cake but not both, and in either case in the middle, you get one of the two, that's false. The waiter did not fulfill what you asked for. And if the waiter brings you neither, that's also false. So the way I think about it is an and is only true if both pieces are true. So there's only one place where an and is true. All the other cases of an and are false, and there are four possibilities. Both true, both false, and then a variation on one or the other being true or false. And this is called a truth table. I told you earlier we'll be talking about truth tables. Truth table just lays out every possible truth value that could happen with a certain situation. Now let's talk about the or. With an or, you don't necessarily expect both things to be true. If I say I want cake or ice cream, then if the waiter brings one or the other, that's okay. And if the waiter brings both, then that's okay too. So if we let P be like getting the cake and Q being the ice cream, in the first case here, you get cake and ice cream, then that would be true. But if you're doing or, you don't have to get both for it to be true. I asked for cake or ice cream, so if you get either one, that's okay, it's still true. But look at the last case. In the last case, you're not getting either. And for an or, that is literally the only time that an or statement or a disjunction is false. I'm not good at memorizing things, so I tend not to memorize the tables themselves. I tend to just remember these little, what I call memory aids, these little short sentences. So if somebody asks me about an and, what I do is I just remember this phrase. And is only true if they're both true, or is only false if they're both false. And those are my memory aids. That's much easier to remember than trying to remember the entire table over here. That's just me. You can do it any way you want to, but you have to be good at knowing those truth values. To me, learning these little memory phrases is much better than trying to memorize these whole tables. Literally memorizing everything in a table. Let's do some practice. What if I said 5 is a whole number and 5 is an even number? That's a compound statement. The first statement is 5 is a whole number. Remember, your whole numbers are your counting numbers plus 0. Well, 5 is a counting number, so that means it's also a whole number, so that's true. Second part says 5 is an even number. Well, everyone knows 5 is odd, so that's false. And you're doing an and remember, an and is only true if they're both true. Well, they're both not true here, so the statement is false. Easy, right? How about this one? 2 is a prime number and 2 is an even number. Now, if you're a little rusty on your primes, you've got to remember a prime number, the smallest prime number is 2, and then it consists of all the numbers, all the counting numbers that can only be divided by the number itself and 1. So 6 is not prime because 6 can be written as 3 times 2. 7 is prime because the only way you can factor that is 7 times 1. So 2 is the smallest prime, and if you didn't know that, you might want to take a minute to Google prime numbers and look back over those. But that's true. Second part says 2 is an even number. Again, that's true. And you've got an and again, and is true only if they're both true. Well, they are both true, so that statement would be true. Easy, right? How about this one? Now let's change ands to ors. 5 is a whole number or 5 is an even number. Well, again, we've already talked about the fact that 5 is a whole number and that 5 is not even. But this time we're doing or. But an or only has to have one piece to be true for the whole thing to be true, because or is only false if they're both false. Well, they're not both false here, so that statement's true. 4 is a prime number or 3 is an even number. Well, 4 can be written as 2 times 2. It's not prime, so that's false. 3 is not an even number. It's an odd number, so that's false. Or is only false if they're both false. Well, here they are both false, so this statement is false. Practice makes perfect. You have to practice this stuff.